In this video, we're going to discuss gas laws, which are a series of equations that allow us to calculate the pressure, volume, temperature, and amount of gas present in every sample. These laws are built off of the concepts of kinetic molecular theory. If you have not already talked about this in class and or watched the video at home, I recommend you watch that video first and then come back to this video later when you're better prepared. We'll begin with a list of learning objectives for the videos. Basically, only thing we're going to cover in this video are the actual gas law equations themselves, and there's a bunch of them. We have the ideal gas law equation, Boyles Law, Charles Law, the Gay-lassac Law, and the combined gas law, which pulls a bunch of them together. A little separate, but along the same lines, we're also going to talk about Dalton's Law and finally Graham's Law. In the video, we're going to focus on just the equations. In class, we're going to talk more about how to use these equations in order to do the actual calculations we're looking for. Before we begin, we're going to start with a discussion of what gas laws are in general, so we have some formal definitions down. Basically what they are, as I've already said, is a series of equations based on kinetic molecular theory that allow us to mathematically calculate the pressure, temperature, volume, and amount of gas present in an ideal gas sample. These formulas, or these equations, were determined by many different scientists over many years, and we're going to try and go over as many as we can relatively quickly. And again, it's also important to realize that these predictions, or these mathematical formulas, match the predictions and postulates of kinetic molecular theory. Now again, they were made mostly before kinetic molecular theory exists, but the observations in the lab very closely match the observations made in kinetic molecular theory, again pointing to the fact that this is all pretty good science. With that, we're going to dive right into our first equation. This is the main central equation. This equation could be used for pretty much any scenario possible. However, in a lot of cases, there are other equations that work better given the situation you're working with. This equation is known as the ideal gas law, and it's probably one of the most iconic of the group. The equation we're interested in right now is PV is equal to N times R times T. Now in previous videos we've already defined what all these variables are except for one of them, and those things still stand. P is our pressure, V is our volume, N is the amount of gas, and T is the temperature of our gas. We have an extra variable here, this letter R. R is our gas law constant. Pressure and volume are not equal to the product of numbers of moles and temperature, but they're proportional. And the ratio that connects that proportion together is the value R. To determine this value, scientists did lots and lots of experiments with real gases. They recorded pressure, volume, numbers of moles and temperatures, and solved for that value of R. And over many iterations, we found that that value of R is 0.08206. And here's the interesting part, the unit, liter atmospheres per mole Kelvin. So it's got a very complex unit that goes along with it. The reason that complex unit is there is because it has to match the units from the rest of the problem. That gives us the big warning about the ideal gas law equation, is that it is very unit specific. Whenever you're working with this equation, your units that you use for your variables have to match the unit that shows up in the value of R. And we'll actually talk about other values R you can use with different units. Anyway, our pressure here has to be in atmospheres. That's a unit of pressure. Our volume here has to be in liters. That's something we work with all year. N, the amount of gas, has to be in the unit of moles. And then finally, T has to be in the unit of Kelvin. If you've got all of your values in the correct unit, if you've got the correct value of R, you can plug in any of the variables you want and solve for whatever variable is missing. Again, in this video, we're focusing just on the equations themselves. We'll go through some calculation examples together in class. This then brings us to our next law. You'll find these next couple laws are all derivations from the ideal gas law equation. It's going to pull out just a couple of variables at a time. Before we start, we'll talk about the scientist himself. This is a scientist by the name of Robert Boyle, an Irish physicist / chemist. One of his most notable achievements, aside from Boyle's Law, is he was one of the first proponents of the scientific method itself. Prior to that, scientists reported on what they thought was right, Robert Boyle spent a lot of time arguing with them, saying we shouldn't talk about what we think is right, we should talk about what we have evidence to support what is right, which is the cornerstone of how we do science today. Now, more pertinent to what we're dealing with now, Robert Boyle is credited with the discovery or the creation of Boyle's Law. There's actually a little controversy going along with that. There are actually a couple other scientists less notable than he was that did the majority of this work. He just happened to be the richest, most notable person involved in the process, ergo the name kind of goes along with him. What is important, though, is that there was a discovery made, and that was the relationship between the pressure and volume of a gas at constant temperature and constant quantity of gas. And that equation looks like this one. P1V1 equals P2V2. What this means is that if we know the pressure and volume of a gas sample initially, and then one of those two variables changes, i.e. the tank gets smaller or the pressure gets higher, we can then calculate a new pressure and volume afterwards by plugging in the new pressure and solving for the new volume, or plugging in the new volume and solving for the new pressure. This is kind of a before and after scenario here. Unlike the ideal gas law equation, this is much less unit specific. The only big rule you have to worry about with equations like this is units must match. Doesn't matter what pressure and volume unit you use, as long as it's the same on both sides. Our next law goes by the name of Charles' Law. Again, we'll start with a quick rundown of the scientist himself. This scientist is Jacques Charles, a French scientist. He kind of dabbled in a lot of things. Most notably, he did a lot of work with ballooning, hot air ballooning. If you recall back in the day, this is one of the first forms of flight, and he was very much involved with it. Charles' Law basically was a discovery that relates together the volume and temperature of gas, assuming constant pressure and constant amount of gas. And you can imagine how a balloonist like Charles would be very interested in the temperature and volumes of gases in order to fill his balloons properly and get the correct buoyancy. Anyway, his law is just like Boyle's law in the sense that it has the before and after conditions. So again, the ones denote our before scenario, and the twos denote our after scenario, basically telling us if we know the volume and temperature initially of a gas, and then one of those two things changes, we'll then be able to calculate the new temperature or the new volume as a result of this. So we end up getting Charles' Law here. Again, the units are not super duper problematic here. The units must match, just like before, and temperature must be in Kelvin. And you'll find that this is true for all of our gas laws that contain temperature. That temperature must be in Kelvin for this to work. Continue our process through our different laws here. The next law in line is the Gay-lassac Law. Originally, for a long time, I thought this was two scientists working together, and it turns out, now that I had to make the video and do a little more research, it's actually one scientist with a hyphenated name. Joseph Gay-Lassac, another French chemist, physicist, another balloonist. Again, gases and buoyancy were very interesting to these guys as they were trying to discover the secrets of flight, basically. In the Gay-Lassac Law, he found the relationship between the pressure of a gas and its temperature, again assuming constant volume and constant quantity of gas itself. His equation, very similar to the last one, is P1 over T1 equals P2 over T2. Again, we have our before and after scenario, so we can calculate how a change in pressure would affect the temperature of a gas, or a change in temperature would affect the pressure. And just like before, we have to make sure that our units match. And we have to make sure that our temperature is in the unit of Kelvin. If those two things are fine, you should get good answers from the Gay-Lassac Law. Wrapping the basic laws up, we have one last law known as the combined gas law, and as you might imagine, it takes a lot of the laws from before, combines them together to make something a little bit bigger. We're going to take the laws from our three scientists, we're going to blend them together, and we get something known as the combined gas laws. And just like before, we have our, again, before and after scenarios. We have to make sure that units match on both sides of the process, and we have to make sure that our temperatures here are in the unit of Kelvin. And just like before, if you make sure all these things are happening, this will give you very accurate and predictable results. Before we wrap things up, there are actually two more laws. I treat these a little bit differently than the previous ones because they behave a little bit differently than the previous ones. The first of these newer and different laws is by the name of Dalton's Law. And that name, hopefully, is a little bit familiar because we are familiar with this gentleman. This is our good old friend John Dalton, the person considered to be the father of modern atomic chemistry. If you recall, John Dalton did a little bit of everything, and gases was one of the many brilliant achievements that are checked off to his name. What Dalton's Law talks about is the total pressure of a mixture of gases. So we have a bunch of gases combined is the sum of the pressures exerted by each individual gas. So if you've got 3 gases in a tank, each one of them exerts its own individual pressure. The total pressure in the tank is the sum of those gases. Basically what we're saying is that pressures are additive. These pressures have a name. They're known as partial pressures, and the definition for partial pressure is already up here. It is the pressure exerted by an individual gas in a mixture. So if you take those individual gases and look at their pressures alone, that's your partial pressure. The name or the description there kind of tells you what the equation is, but just to make sure we have it written down on paper, it's right here. The total pressure in our sample here is equal to the sum of all the partial pressures. And depending on how many gases you have mixed together, you're going to have different numbers of partial pressures. But that's what all these p-values here are all about. These are our partial pressures. So if you get a bunch of pressures in a problem, it's very simple to add them up. If you're given some pressures in a problem and a total, it's very easy to solve for the missing pressure. And then you might be asked to take that information, plug it back into one of our other equations to calculate the volume of that gas, the temperature of that gas, etc., 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 as being separate from the other group. Last but not least, we have Graham's Law. Graham's Law is unfortunately the strangest of the group, but the nice thing about Graham's Law is it is so much different than the others, it is very, very easy to spot. Everything else deals with pressures, volumes, temperatures, and moles. Graham's Law deals with rates and is a totally different beast. That rate that we're interested in is a rate of diffusion. And this is something you should have talked about back in bio when you talked about water and other molecules diffusing across a cell membrane. And in diffusion, no matter what it is, it's a movement of a gas from a high concentration to a low concentration. So if you have concentrated gas over here, it's going to spread out and fill up the low concentration area until everyone has the same concentration. Again, going back to bio, we had concentrations of solutes in water, and water would move back and forth across the membrane until eventually those concentrations equalized. The reason this happens is because of entropy. It is highly unlikely that all of your particles will be clustered over in one area and not spread out. As random events start occurring, the natural tendency of that cluster of particles is to spread and evenly spread themselves out across the entire group. So it's a driving force like in chemical reactions, and entropy is a driving force here in this process as well. What this does is it causes gases and other substances to mix with one another. A great example could be sample of perfume. So say we're in the corner of the room here, and I use my little perfume bottle and spray a little puff of perfume. This is the rest of the gases filling the room. Over time, these perfume molecules are going to diffuse throughout the room until they are evenly distributed throughout the entire container. That's why I can spray perfume in the corner of the room, and 2 minutes later, you on the other side of the room will eventually smell it. This is an also great explanation for why balloons behave differently. If you've ever been to a party, you can get balloons in 2 major flavors here. We can have latex balloons, or we can have mylar balloons. These are the rubbery ones. These are the silvery ones. A rubber balloon or a latex balloon filled with helium gas will fall to the ground within 24 hours. This is because the helium diffuses through the latex and escapes into the room around it. That helium escapes or diffuses so quickly, the end result is that the balloon deflates quickly and falls to the ground. The mylar balloon, on the other hand, the material made in this balloon does not allow helium to sneak through very quickly, and as a result, these balloons last for weeks and even months in some situations. So what we can see here, and this gets more into Graham's Law, is that helium diffuses through these balloon membranes quicker with latex and diffuses slower with mylar. Continuing that discussion of rates, we get into the actual rule or the actual discussion of Graham's Law itself. The relative rate at which two gases diffuse is proportional only to their molar masses, meaning this gas diffuses quickly, that gas diffuses slowly. The only thing that links the two of them together is what their actual molar masses are. And we can get a little more specific. Heavy gases, ones that have large molar masses, tend to move and diffuse slowly, whereas light gas particles tend to move quickly and diffuse more quickly as well. This is all based off of some physics from last year. Kinetic energy is equal to 1/2 mv squared, and if you recall, kinetic energy is proportional to temperature. When we have two gases mixing together, they tend to be at the same temperature. If the mass of one gas is very high, that's going to mean its volume is going to be, or sorry, its velocity, not volume, is going to be relatively slow so that we equal this same constant temperature value. Likewise, if the mass of one of our particles is very, very low, we would expect its velocity to be much higher, again at a constant value for t. So we can have a mathematical expression or explanation for why this actually works. This mathematical equation also then leads us to the actual formula that goes along with Graham's law. These two rates over here can be rates of diffusion, or as we'll talk about in class, rates of lots of different things. And we can see that these rates are equal only to the square root of the molar masses of the two samples. The one thing to watch out for this equation, though, it's rate A over rate B, your two different samples, but the molar masses end up being B over A. If we have more time, we'll take some time in class to derive this equation and show why it ends up being like this, but for now, you just need to be comfortable with using the equation itself. Well, that's pretty much it. Again, the only purpose of this video was to list out the actual equations themselves and give you a little historical context as to where they came from. And that's really what you should be able to do at this point in time. You should be able to define and explain what gas laws themselves are, a series of equations based on kinetic molecular theory that allows us to calculate things like pressure, temperature, volume, and moles. You should be able to identify the 6 gas law equations themselves and briefly explain what they are. I don't expect you to have the equations memorized, but you should recognize what equation does what. And in class then, what we haven't talked about is the actual use of these equations, plugging in numbers and actual getting answers. In most cases, it's just simple algebra. In some situations, it's a little bit tricky. Either way, we have plenty of practice problems to work on in the near future. We'll be putting our calculators and these equations to use to make the necessary calculations to figure out the properties of these gas samples.